Look at the sheer footprint of a utility-scale solar array. You are looking at thousands of individual panels sprawling across miles of desert. Monitoring a system this vast physically is a logistical impossibility. You cannot deploy a team of engineers to walk the grid, checking the voltage, temperature, and output of every single node, sensor, and inverter. Instead, the operation of this entire geographic footprint must be concentrated into a single, centralized control room. To execute that level of control at scale, you need a digital bridge that pulls raw, physical field data and translates it into actionable intelligence. That architecture is SCADA, Supervisory Control and Data Acquisition. Organizations like Devi Automation Solutions use this specific framework as the architectural blueprint for modern industrial design. SCADA functions as a multi-layered ecosystem of hardware and software components working in tight synchronization. We are going to deconstruct this ecosystem from first principles. By building the SCADA pipeline from the ground up, we can trace exactly how physical data moves from the field directly to the control room. Let's start at the foundational physical layer using a municipal water treatment plant. Here is a basic, isolated water tank and piping system. The first component we need is a way to measure reality. Sensors are deployed to capture raw, analog data, like the current water level or the flow rate through the pipes. We also need a way to affect reality. Actuators, such as mechanical pumps or motorized valves, execute the physical changes required by the system. To manage these devices locally, we wire them directly into a programmable logic controller, or PLC. The PLC serves as the local brain. It reads the sensor inputs and autonomously executes isolated control loops, deciding to turn the pump on or off based on the tank's water level. But a PLC only knows about the specific hardware wired directly into it. If it operates in total isolation, it cannot coordinate its pump with the broader demands of the entire municipal water network. To solve this, the PLC must digitize those localized analog signals and package them for outward transmission. The data then enters the industrial communication network, the critical transport layer of the architecture. This network acts as a highway, standardizing and transporting data streams from dozens or hundreds of distributed PLCs simultaneously. At the top of this digital pipeline sits the central brain of the architecture, the SCADA server. The server constantly receives, aggregates, and intelligently routes the continuous influx of field data coming from across the entire plant. This makes the SCADA server the link between the operational technology in the physical field and the information technology processing in the control room. To make this aggregated data legible to a human, the server feeds it into a human-machine interface, or HMI. Simultaneously, data is routed to the historian database, which archives the information for long-term storage and analysis. We can see exactly how this full pipeline operates by introducing a mechanical failure in the field. Watch what happens when a primary water pump suddenly seizes. That failure registers at the PLC, fires up the communication network, hits the SCADA server, and instantly triggers a visual alarm on the operator's HMI. The operator assesses the situation and inputs a supervisory override command right from their workstation. The command travels back down the exact same pipeline, from the server, through the network, and into the local PLC, instructing it to activate a secondary backup pump. By enabling this command and response cycle, SCADA functions as a continuous, closed-loop pipeline for instantaneous fault correction. Let's shift our focus from a reactive fault in a water plant back to a macro-scale operation, like a massive solar facility. Here, the system is continuously tracking a matrix of variables: panel voltage, electrical current, inverter status, and live weather conditions. While catching a failed pump is important, the highest value of SCADA at this scale is the shift from reactive fault management to predictive maintenance. This chart shows the correlation between voltage, temperature, and time. By querying the historian database, operators can spot microscopic downward trends in an inverter's voltage over a period of months. Through this historical trend analysis, the control system functions as a proactive intelligence engine, allowing engineers to replace degrading components long before a critical failure halts power generation. Centralizing control over physical infrastructure does create inherent vulnerability. If the network goes down or is compromised, the entire facility is blinded. Implementing this architecture requires deploying secured, isolated communication networks and enforcing strict user authentication protocols at every point of access. Operational continuity demands regular database backups and the continuous testing of the communication loops between the PLCs and the main servers. The software itself must be maintained with security patches to guard the facility against industrial cyber threats. When properly secured, SCADA provides the digital framework that makes complex manufacturing, massive power generation, and smart agriculture possible. Mastering these systems requires a technical grasp of how digital commands translate into physical outcomes, the essential requirement for designing automated infrastructure.